The famous shaped circle has a long history, but one particular invention, the wheel, was the first to explore the properties of the circle. In theory, since a circle only has curved lines, it only comes into contact with the ground at one point, also known as a tangent. Because of this small point of contact, instead of sliding sideways, the point is moving up and down instead. As a result, the wheels are able to turn instead of slide on the ground, which is why the friction between the wheel and the ground is significantly reduced. Another property that the wheel is using is the fact that every point along the wheel has the same distance from its axle. This makes the force required for turning the wheel even at all times, as well as making sure that the height of the carriage is even throughout the ride. Okay, so from the story of the wheel, we can come up with a pretty simple but robust definition for a circle. A circle is a shape in which every point along the boundary are the same distance from the center. The distance between the center and the boundary is called the radius, which is the same all along the circle. Another thing that I've mentioned in the history of the wheels are tangent points, or basically where a circle meets a line. And here is where we meet our first property of the circle. Imagine you are standing in the center of a square room. You see a circle on the floor going all around you, barely touching the walls of the room. If you were to touch the walls as fast as possible, what is the quickest way? Obviously, you would face the wall and start running towards it. Your line of sight will be perpendicular to the walls. At the same time, if you look from the center of the circle, in which direction is the shortest way to touch the wall? If you guess the radius that is tangent to the wall, then you are absolutely right, since it's already touching the wall in the first place. If you had gone in any other direction, you would need to take extra steps to touch the wall. So, what property are we trying to derive from this whole ordeal? Well, the radius of a circle is perpendicular to its tangent at that point. Let's prove this more rigorously, without the story part. Say we have a circle at point O. The shortest distance between O and the tangent is the segment OP. Now, obviously OP is perpendicular to the tangent. Say we have another point Q along the tangent line. How do we minimize the length of OQ? Well, the same way we touch the wall the fastest, if we have Q on the left or the right side of the tangent, the length OQ will be the radius plus some distance away, unless we set Q to be the same as P, which is the tangent point. In which case, the length of OQ will be the radius. Hence, we have rigorously proven that the radius is perpendicular to the tangent. Another fascinating property of the circle is that the distance of two tangents from a point, let's say point P, is always the same. To prove it rigorously, draw a circle with the center O and another point P. Now, you can draw the line of symmetry between OP. Notice that the radius of the circle remains constant. The length of OP is also constant, and both tangents are perpendicular to their respective radiuses. Because of the Pythagorean theory, we can deduce that the tangents are exactly the same length. So far, we've been discussing things outside the circle and how it interacts with the circle. But what about the circle itself? Well, this is one of the oldest experiments in the book. Get a circular container and some strings. If you wrap the string around the container once, you get the perimeter. Now measure the length of that perimeter. Now, measure the diameter of the circle either using a ruler or another piece of string. Lastly, divide the perimeter of the circle by the diameter of the circle based on your measurement. You should get something around 3.141 something. Or if you're looking at the length of the strings, the perimeter should be about 3 times as long as the diameter. Repeat this process with different circular containers that you can find in your house. Every time, you should be able to get around the same value, that is 3.14159 followed by a lot of random numbers behind it. Now, this constant holds true for circles of all sizes. This number is so special that mathematicians named it after the Greek letter pi, and if you work backwards, you can figure out how the perimeter of the circle is basically pi multiplied by its diameter. Now, hold this constant for a while because it's going to be important in the coming videos. Now, imagine you're in an art exhibition, standing at the edge of a circular room. You see a large painting in front of you. Your friend chose to be annoying that day, so he stands in the middle of the circular room to block your view. Both of you are trying to see the painting from end to end, but notice that your friend has to turn his head in a much wider angle than you, because he's standing in the center of the circle. As a matter of fact, the angle your friend has to turn his head is exactly twice the angle you have to turn your head. Don't believe me? Let's prove it. Draw the room you're standing in as a normal circle, you as a point along the perimeter P and your friend as the center O. Label the ends of the painting A and B. Now, draw a line from P to O and extend it until it meets the circle, say at point Q. Label angle APO angle A and notice how triangle POA is isosceles. Therefore, you can quickly determine the rest of the angles of the triangle in terms of A. But most importantly, you can determine the angle LQ, which is 2A. Now, repeat the steps, but this time with triangle POB. Let angle BPO be B, calculate the angles in the triangle PPO, and you will arrive at the conclusion that angle POQ is 2B. Now, the angle at which you turn your head is basically angle APO plus angle BPO, which is A plus B. And your friend has to turn his head at angle AOQ plus angle POQ, which is basically 2A plus 2B, or twice what you have to turn your head. You just proved that the angle at the center of the circle is twice the angle at the circumference of that circle. Now you know all about the angles inside and outside of the circle, as well as side lengths inside and outside of a circle. You can now prove all other circle properties that you will ever come across. For example, let's go back to the art exhibition. This time, you brought another friend who is also standing at the perimeter of the room, blocked by the same annoying friend of yours that stands in the center of the room. By the same logic, to see from end to end, the friend in the center has to turn his head twice as large than the friend standing in the edge of the room. This is another property of the circle. Angles facing the same segments are equally large. Segment is basically a part of the perimeter of the circle. Now, imagine the painting covering half the room. Your friend in the center will have to turn 180 degrees to see the painting, while you only need to turn 90 degrees to see the whole painting. Notice that between your friend's old line of sight and his new line of sight, it forms a diameter, or a line that passes through the center of the circle. As you can see visually, diameters are twice the length of radius of the circle. So here comes another property. Given a triangle whose corners lie on the perimeter of the circle, the triangle is a right-angled triangle if and only if one of its sides is the diameter. As you can tell, this is nothing but a special case of the center angle being twice as large as the circumference angle. Now imagine two paintings is covering the whole room. You and your friend stands on the perimeter facing each other, while that annoying friend of yours still stands in the middle of the room. To see one of the painting, your friend in the middle has to turn twice as large compared to you. Then, when he wants to see the other painting, he needs to continue turning. His angle of rotation will be twice as large as your other friends. If you're to add your angle of rotation with your friends in the opposite side of the room's angle of rotation, how much would it be? Well, your annoying friend in the middle of the room rotates 360 degrees, or the whole room, which is essentially twice the sum of the angle of you and your other friend's turn. So, the sum of angle of rotation between you and your friends in the opposite side of the room is basically 180 degrees. Simple. With this, you just unlock another property. If there is a quadrilateral, or basically a four-sided shape inside a circle, whose corners are on the perimeter, the sum of two opposite angles are always 180 degrees. Now, there are a lot more properties of the circle that is not covered in this video due to a lack of time and, well, a lack of analogies. Another important property that you will likely encounter in your mathematical journey is the alternate segment theorem. If you go down in the description box, you should see a link where you can read more about this fascinating property. Okay, so let's recap. Today we've learned about the definition and some properties of the circle. A circle is basically a closed shape that has equal distance, called the radius, from its center to all points along its perimeter. The tangent of the circle is always perpendicular to the radius at that tangent. We also learned that the angle at the center of a circle is twice as large as the angle along the perimeter, which is the same everywhere given they are facing the same segment. However, if two angles are facing opposite segments, like in two painting analogy I gave, the sum of those angles are always 180 degrees. Thank you all for joining us today. I hope you like our content. If you do, make sure to hit like and subscribe and leave a comment down below. We'll see you soon.